Okay, I'm presenting the model solution for your third coursework. You had to write a MATLAB program that will solve a general beam problem. The beam is of length L, has any number of loads on it, applied loads on it, W1, W2, W3 up to Wn, at distance of P1, P2, P3 up to Pn, respectively from the left hand end A, and the beam also has its own weight, which is uniform and is W per unit length. The positive directions of the loads, the applied loads, is downwards. Therefore, if W2 is minus 20 kilonewtons, that means that at x equals P2, you have a load of 20 kilonewtons pointing upwards. Whereas if W2 was 20 kilonewtons, then at x equals P2, you have a load of 20 kilonewtons pointing downwards. The formula that you had to use was this one here, okay, which is saying that the bending moment distribution is the superposition of these bending moment distributions there. So the bending moment distribution, that is the bending moment at a distance, at a general distance x from the left hand end of the beam, is the superposition of these bending moment distributions. This is the bending moment distribution due to the weight, to the distributed weight of the beam on its own. And mk of x is the bending moment distribution due to the concentrated load wk applied at a distance of pk on its own, with all the other loads removed. Okay? And this is the expression for the bending moment distribution due to the weight of the beam on its own, with all the applied loads removed. And this is the bending moment distribution due to a single concentrated load of wk at a distance of pk from the left hand end, with all the other loads removed and not considering the weight of the beam. Okay? Now the program had to do a graph of the total bending moment versus x. Okay, total bending moment versus x, where x is the distance from the left hand end. So what you are doing here, okay, was illustrated. So basically it's an illustration with 3 loads, okay, as an example. This is m0 of x, the bending moment distribution due to the weight of the beam on its own, with the applied load removed. This is the bending moment distribution due to the load W1 acting on its own, with the weight of the beam neglected. And this is the bending moment distribution to the load W2 acting on its own, and so on. So the principle of superposition tells you that the bending moment distribution at any given position is the superposition, is the sum of the bending moments contributed by these different distributions. So you need to add these bending moment distributions together. Okay? That is what the program needs to do. So this is the program that you have to write. So if we go back to the requirements of the question, the program had to be able to solve the general beam problem, that is, handle a beam of any length, any weight per unit length W, with any number n of applied loads of whatever value and position. The program should have the facility to input the data interactively, from the user to input the beam length, the weight per unit length, and the value and position of each applied load. And the MATLAB figure generated by your program should be titled and the axis appropriately labeled. So if we go, that is the program that you should have written. Okay, how do you write it? You write it in the editor window. So if you are at the command window, you type new script, you have the editor window, and then you start writing clear all variables, and write the L equals input, enter length of beam, blah blah blah, in meters, and so on. Okay, and this is the program. So here you're using the input function to enter the length, the number of loads, the weight per unit length, and I've used a for loop here so that the user is prompted to enter each individual load and its position. However, you could have entered the loads all at once as a vector. Okay, so the user, instead of being prompted to enter each individual load one at a time and its position, you could prompt the user to enter all the loads as a vector. Okay, and then all their positions as a vector. That is fine. And then your program needs to plot a graph of m, the bending moment, versus x. Therefore, in order to plot, you need to have a vector of x coordinates and a vector of y coordinates. So you need to create a vector of x coordinates before you can create the corresponding vector of y coordinates and plot the vector of y coordinates against the vector of x coordinates. So we start by creating a vector of x coordinates. So for the multiple choice, you were told that the spacing needs to be L over 1000. Therefore, if the spacing is L over 1000, so you have 1000 spaces, that means you have 1001 points. Okay, therefore if you're using linspace, the number of points should be 1001. If you have 1000 subdivisions, that means you have 1001 points. Okay, if you had 2 subdivisions, that means you have 3 points. If you have 1000 subdivisions, then you have 1001 points. And with linspace you specify the number of points, the first value of x and the last value of x. So that means create a vector in the range 0 to L, with the first element being 0 and the last element being L, and the vectors to have 1001 points. Alternatively, you could have created it like this: x, create a vector in the range 0 to L, with the first element being 0, in increments of L over 1000. So create a vector in the range 0 to L, in increments of L over 1000, with the first element being definitely 0. Okay? Both commands produce identical vectors. Now this is the m naught. Notice x is a vector. L minus x is also a vector. And in order to multiply the corresponding terms of vectors, you need the dot times. Okay, you need dot times. So this here is a quick way of doing this formula here. 0.5 wx times L minus x. Okay. Now m is the vector of bending moment distributions that you are ultimately, the vector m is the vector containing the bending moment distribution that's ultimately going to be plotted against x. So initially it will have m naught, but we're going to continually add, alright, we're going to continually add to m the bending moment distributions from the individual loads, in addition to the bending moment distribution due to the distributed weight of the beam. Okay, so initially m contains, it holds the bending moment distribution due to the weight of the beam acting on its own, but I'm going to add to it, I'm going to update it with the bending moment distributions due to the individual loads, because I'm going to create a loop. I have a loop there, and every time the loop is entered, m is going to be updated. Alright, it's going to have a bending moment distribution added to it, a bending moment distribution from an individual load. Okay, from an individual load. So for k equals 1 to n, for k equals 1 to n, so k is a scalar counter, and every time the loop is entered, k will have a different value. It starts with 1 and increases up to n, where n is the number of loads. That's where the loop terminates. Okay, every time the loop is entered, I'm going to add to m, I'm going to update m with the bending moment distribution from an individual load. Okay, so in general I'll have a load of wk, okay, which is the kth element of w. W is a vector, capital W, okay. Small w is the weight per unit length. Capital W is a vector, okay. Element number k of w, okay, that's wk. Now the bending moment distribution due to wk is in two parts, okay. For points, for positions that are to the left of the load, you have this bending moment distribution. For positions that are to the right of the load, you have this. So the bending moment distribution of wk, it is in two parts, as you well know. Okay, if you look at the video, you can see it. It's in two parts. One part and then another part. One part to the left of the load, another part to the right of the load. And these two parts are described by different equations. Now, what I need to do is to split the vector. Okay, the vector of x coordinates. I need to split it. And this is how it's done. So x is a vector there. A is p of k. So for simplicity, I'm going to say that p of k, the position of load number k, so I'm focusing on load number k, the position of load number k is A. I find those elements of x that are less than or equal to A. Okay, those elements of x that are less than or equal to k. What is the index of those elements of x that are less than or equal to k? So I've used the find function and I've applied that condition there, and f1 gives me the element, the indices, right, of those elements of x that are less than or equal to k. Likewise, f2 is a vector of indices of those elements of x that are greater those elements of x whose values are greater than a. Okay, so f1 is a vector of indices of those elements of x whose values are less than a, so those elements of x that are to the left of load wk, and f2 is the vector of indices of those elements of x that are to the right of load number k. Okay, now the x coordinates themselves, remember f1 and f2 are vectors of indices. The sub-vectors of x that are respectively to the left and to the right will be given by x of f1 and x of f2. So x1 is the vector of the values of those elements of x, the actual values, not their positions, that are to the left of wk, and x2 is that subvector of x containing those values of x that are to the right of load wk. Okay, so I've split x into two subvectors. This subvector, I use it in order to evaluate this equation. So for this equation I use subvector x2, for this equation I use subvector x1. Sorry, for this equation I use subvector x1, and for this equation I use subvector x2. Okay, let me say that again. For this equation I use subvector x1, and for this equation I use subvector x2, and that is exactly what I'm doing here. Okay, this equation there and this equation there, and notice m1 is a vector and m2 is a vector. Okay, m1 is a vector containing this part of bending moment distribution, and m2 is a vector containing this part of bending moment distribution. Okay, but that is done for all elements. Now I join m1 and m2 together like this in square brackets, okay, and then add that vector to the current value of m. So take the current vector m and update it with the bending moment distribution due to load number k. Okay, load number k, which is composed of two parts, like I said, a part to the left of the load and a part to the right of the load. The part to the left and the part to the right are joined by square brackets like this. Okay, and that resulting bending moment distribution due to load number k on its own is added to the current bending moment distribution. So every time m is being updated, every time you go to the loop. Where in the tutorial sheets do you know how to do this? Do you learn how to do this? Combining two vectors together into one long vector. So one row vector combined with another row vector using square brackets to create a composite vector. That is found from tutorial 2. Page 9 if I'm not mistaken there. Okay, It's over there. Also, where do you learn this trick? In which tutorial sheet? In tutorial 4 itself, you had an example. This function, heaviside function, where you had the function was in two parts, one to the left of x0 and one to the right of x0. Okay, a step function. And if you look at the solution, you see it there. K1, vector of indices of those elements of x that are to the left of x0. K2 is the vector of indices of those elements of x that are to the right of x0. X1 is a subvector of those elements of x that are to the left of x0, and that is therefore, x1 is therefore given by x of k1, and x2 is the vector of those elements of x that are to the right of x0, and therefore x2 is x of k2. Okay, and the two parts, the left part and the right part of the distribution, are h1 and h2, and they are given by that. And for h1 you use the subvector x1, and for h2 you use the subvector x2, and then you join them together like that. Okay, side by side, one row and another row, to create the composite distribution. X is also composed of those two parts, and you plot h against x. Okay, this is an example that should have helped you. Okay, do the coursework, the heaviside function. Question number 10. The difference between 10 and 11 is that 11 is slightly more complicated because you need to use a loop to combine more than one distribution, where each distribution, apart from the first one here due to the weight, each distribution from the individual loads is composed of two parts. Okay, so after that you open a figure window and you plot x, m, and you label. Okay, so that is what you had to write. Right, so let us run the program for the specific example. So you had loads there, 1.5 kilonewtons, 3 kilonewtons upwards, so -3, and 2.5 kilonewtons. Distances of 3, 5, and 7. And the weight per unit length is 150 Newton per meter. So let's run. Length of beam 10. Number of applied loads is 3. 150 to 1.5 E3. 3 minus 3 E3. 5 2.5 E3 7. Notice the program must tell the user what units, okay, to use. So make sure that in your input interface you specify to the user what units to use. That is the bending moment distribution there. Okay. So your coursework quiz requested you to find the value of the bending moment at specific locations, and I'm going to show you how to do this using the zoom and data tips facility. Now, like I said, the buttons for zoom and data tips facility, they are on the top right hand corner of the white area of the graph, and they will only appear if you navigate with your mouse into the white area. Okay, you will see them appearing. If you navigate out, they disappear. Okay, so we need the value of bending moment at x equals 2. So you click zoom and it becomes blue. You magnify the area by clicking and dragging. You then click on the data tips. It turns blue. And you click. Suppose you click at the wrong point. That is not the point where I want it. It's not x equals 2, it's x 1.99. You can eliminate that label there if you right click and then click, you right click on it and then click on delete current data tip. It will disappear, and then hopefully you click on the right place. X equals 2, y equals 1800. Okay. You can right click on that and remove that current data tip. Okay, delete it, but I'm going to leave it there. Anyway, now I need to restore the original view of the graph. So you click on zoom and then right click at any point on the white area. Okay, and then click on restore view, and we have the graph as it was. Okay, x equals 3. X equals 3. That is relatively easy. I'm still going to use the zoom. We're still in zoom mode because the zoom button is blue. I magnify that area, and then with the data tips, I click on data tips and click there, and I have when x equals 3, y equals 2475. I restore the original view. I click on the zoom. I then right click at any point in the white area and click on restore view. The next location is x equals 5. That's also easy. I'll use the zoom. I'm in zoom mode there. And then click on data tips and then click here, x equals 5, y equals 3.375, sorry. Okay, restore the original view by clicking on zoom and then right click and then restore view. X equals 6, a bit tricky. Okay, I'm going to use the zoom. We're in zoom mode. Magnify the area. Click on data tips. Suppose we click on the wrong position here, 5.99. That's not the position we want. Right click on it and then delete current data tip. And then we try again. Again, delete, right click on it, delete current data tip. That's not the point we wanted. I'm going to try one more time. Hopefully it comes out right. There it is. X equals 6, y equals 2100. That is the answer. That was what was required. That was required. We click on the zoom and then zoom out. Right click at any point on the white area and then, sorry, zoom out, or actually restore view. And we have the graph reappearing. The next position is x equals 7. Click on data tips. I don't need to zoom there. Oops, I do need, well, I made a mistake. It's 7.01. Delete current data tip. I'll try again. If I fail, I will use the zoom. Okay. 7. At x equals 7, y equals 3675. That is what was required. X equals 9. X equals 9. I use the zoom. Click on zoom. magnify the area. Click on data tips. Mistake. Right click on it, delete current data tip. I will try again. Again, delete current data tip. Right click on it and delete current data tip. Try one more time. If not, I can get a larger zoom, okay? Magnify it even more, decreasing the likelihood that I make a mistake. And now there it is, okay? So if you're finding it hard to click on the right point, you can always continue magnifying until you have, you know, a really well-defined area. Let's restore the original view. Click on zoom and then right click at any point on the white area and restore view. One way of helping you click on the correct points is to actually plot the data points, okay? By editing the plot to show the markers. The markers are the points where the data is actually plotted, because remember, the bending moment is plotted at intervals of x equal to 1/1000 of the span, okay? 1/1000 of the span, L/1000. That is the separation in the x direction between the data points, okay? So if we go to edit plot mode, and then left click on the curve, to select it, and then right click with the mouse, and then we go to marker, and we choose a marker, circle. I'm going to use cross. And there you have the data points plotted. If we then go to the zoom, now if you're in edit plot mode, the zoom button does not appear. You need to unclick the edit plot mode, and then the zoom buttons appear if you navigate over the white area, and then you go to the zoom button, and then you zoom, and you can see that the point x equals 9 is clearly identifiable. Let's remove that label there. We go to data tip, we right click on it, delete current data tip, and you can clearly identify the point where x equals 9. You can click on it. Sorry, I made a mistake. Delete current data tip. There it is. That is the point x equals 9. The marker is helping you locate it. And there you have it. Let's restore the original view. Okay. Another way to help you is to use the grid. So if you go to the command window and you type grid on, you will have a grid. And you have a grid line at x equals 9. Therefore, you can easily, if you also use the zoom, you can easily locate the point x equals 9. The grid is in fact the most helpful facility, okay? Because all the positions that were specified in the questions of the coursework quiz coincided with grid lines, okay? And this grid line is helping you locate the correct data point. Okay, thank you for your attention.